Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
I call for the next speaker, will be Professor Hai-Qing Lin, and he will talk about computational physics.
Okay, good afternoon, everyone. Thank you, and thank you for being here at this late time. So in the next 25 minutes, I try to tell you my own view on computational physics. As Professor Jing said, it is mission impossible to tell you an overview, so I just give you my view on computational physics here. So I try to tell you what does computational physics do, what computer simulation is about, then briefly history of development of computer, and then talk about simulation of classical systems, simulation of quantum systems, and the challenge facing the computational physics. Yeah. Okay. So what does computational physics do? Computational physics combines physics, computer science, and applied mathematics. It provides scientific solutions to real-world problems, and it employs common techniques to areas such as material design, environmental modeling, nuclear cleanup, energy management, medical imaging, financing, and etc. Okay. Thank you. Okay. Being a computational physicist, okay, we are not only just understand the working of computers and the relevant science and mathematics, but also we know how to connect them all. And computational physics also enjoys career mixing both high-performance computing and science. And also you can put other things up there. All right, now, in old days, okay, when we deal with classical physics problems, such as Newtonian mechanics, shown here, okay, for this projectile motion, or two-body interaction there, or Maxwell equations. In that time, mostly computers was actually used as a tool to help. Those systems have such characters, such as usually you are dealing with one or a few body problems. It is deterministic because the motion or the whole dynamics can be described by differential equations. The subject of kind of boundary conditions and initial conditions. Then you can make specific predictions once you solve the equations. So computation-wise, it is mostly just like and apply the mathematical problems, and it's just many years for getting some numbers. Okay, actually, it's not what we call now as a simulation in time. Okay. However, as we know the nature more and more, we deal with problems such as nonlinear problem. I show here, for example, a one-dimensional logistic map. In this case, even though this dynamic system is deterministic, it is determined by a single control parameter R. However, you cannot know the number xn without knowing xn minus 1. Okay, you have to go on from the seed, for example, the x0, start going from this logistic map to go to x1, then x2. Okay, you cannot, like before, you simply say, I solve the equation, then I can predict at any time. Actually, you have to go with this sequence to be there. So then from there, you'll see many things you will never or you haven't seen before when you're dealing with classical physics problem, such as bifurcation, and relate this critical phenomena, and also knows something more interesting later, such as I show me here, Lorentz attractor, okay, and then this Mandelbrot set, and also this some other interesting thing. However, those systems, even though it's nonlinear, it's still deterministic. But if we deal with many particles, then even things more complicated will happen. For example, this famous, this n particles in a box. So assuming at the time t equal to 0, you have n particles all on the left side, then you ask yourself, what will be the number of particles on the left after a time t? Okay. Now, ideally, you say, if I have enough computer power, if I know everything, for example, all the conditions, or the boundary conditions, or this reflection coefficient, etc., or how big the hole between left and the right, how big the side, then I may solve the differential equation describing each particle to give a precise prediction of when one particle will be in the left or right. So this, however, as n increases, this becomes impossible. Okay? So people will deal with this problem by different way. So in this case, suppose we're only interested in the behavior from order to disorder, then we will use some kind of simulation, treating the whole process as a random process. Then this random process is, unlike before, is no more a deterministic. It is a non-deterministic now. Okay, and we make a basic assumption such that under the probability, this system, the motion is impossible to predict precisely. However, we make assumption that it is random behavior. Then we can make some progress by simulating this thing using a random number generator. Okay. Now, at this stage, the computer is no longer like before, simply you do numerical analysis, or you simply collect data and do analysis, or you make some graphic, etc. Now, this time, the computer is used as a simulation. Okay. Now, so you, rather than solving the equations, actually, you are doing numerical experiments. You are testing models and algorithms you proposed to deal with the system you are studying. And the way you simulate the system also affects our thinking and also the learning process. And because of this phenomena, nonlinear, non-deterministic, you will meet more of this phenomenon than those linear and deterministic in the nature. So you have to develop some tools to do the simulation. So this time, the computer simulation is very similar to what we perform this lab experiment, perform experiment in the lab. So if I make a comparison here, you see on the left, I have this lab experiment. So you start with sample. You have some kind of physical apparatus to make a measurement. Then you calibrate this physical apparatus to make sure you are getting the right number. Then you do the measurement. Then you do the data analysis. On the right, I will start my computer simulation. First, I must have a model which I believe can give me essential physics behind the phenomena I observe. Then I must have a computer program, so can do the simulation, and this computer program must be testified to make sure it will give you the right answer. Then I do the computation, then I do data analysis. It's very much similar. Okay. So at this stage now, so no more we are using the computers to just solve equations. Now it's different from the old days. Okay. So since the last century, I think the middle of last century, or maybe a little bit later, then the computational physics is not just a helping tool to theoretical physics or experimental physics. Rather, it's become one of the triangles. Okay, so and we all know this triangle become very stable case. Okay, so now it has the same, taking the same weight as you do experimental work and I do computational work. Okay, all right. Now we know the computational physics grows with the development of computer. So let me give you a very quick history. Actually, just give you some data. So the first computer was established in 1946, and here I show you some numbers there. Especially, you can notice that this flops is what we call at each 1 second how many operations it will do. It has 360 flops there. Okay, and at that time, actually, you do multiplication and addition, subtraction at a very different speed there. Now in today, okay, this is top 5 computers in the world. Okay, the number 1 is in Wuxi, China. There, it has IUPAP speed at 93 petaflops. Okay, and theoretically, the peak performance is 128. This is June this year data. Okay, this machine became number 1 in the world already for 3 times. So it started last year, June there. Then the number 2 also made in China, which has been there as a number 1 before Sony for about 3 years. That's is Tianhe 2 case, and it has 34 IUPAP performance, petaflop, and peak 55. Then you have other machines there. All right. So in the top 6 to 10 here, also I listed here just for your reference, in that case, and you'll notice that now the computers, the new computers actually saves power a lot. Okay, if you compare the power, you can see actually this Tianhe 2 takes a lot of energy in that case. So now try to save energy is one important indicator of good computers case there. All right. Okay, so if you look at 10 years ago, all right, this is also top 10 computers in the world. Then you notice that the number 1, the speed is 280 teraflops. Okay, so it's almost 1,000, or if more precisely, 500 faster now compared to 10 years ago. So the old performance looks very much follows what we call Murphy's law. Okay, so this is the log scale inside. Okay. So with this rapid development of hardware, then the computer physics got a very high speed to grow. So let me just tell you, in the old day, in the end of last century, we talked about the success of simulation of classical systems case. Okay, the most notable success is the simulation of many body systems by doing Monte Carlo simulation for the statistical physics. So basically, you want to solve a partition function, because once you know the partition function, you know everything. From there, you can calculate all kinds of thermal averages you like, and the Monte Carlo simulation is a way try to mimic the probability by finite number of samples here. Okay, so a good Monte Carlo scheme will have much less sample numbers than the total, all the possible configurations of the system case. So the task of Monte Carlo is to try to simulate the probability with finite number of samples while getting the right answers case. Okay, so the most successful case or most typical case is so-called the Ising model. In this model, you describe a system by a simple configuration. Say each site you have a spin to tell you the information either up or down. So either 1, 0, or +1 or -1. Then the total energy can be described by this equation in that case, and your task is to find the average at a certain temperature or the ground state when these coupling coefficients are different or different spin configuration are given. All right. Okay. Sorry, 10 or 20? 10. All right. All right. So the development of simulation came from development of algorithms, for example, the Metropolis algorithm, okay, which gives you very easy way to simulate the whole system in the case. I'm not going to go detail their case. So classical Monte Carlo was very successful because it takes easy way to form summations by using random process. Okay, and the most noticeable success is the solution of 3D Ising model because so far we know it's almost impossible to get analytical solutions for 3D Ising model, even though you can do it in 1 and 2 dimensions case there. And during this simulation, you also develop different algorithms because you have to take care of finite size scaling, critical slowing down, universality, frustration, etc. in this problem's case. Right. So now the algorithm development, okay, also came from our understanding of the system, also our understanding of the computer. Okay, because the new computer, also you can do parallel computing, you can do vectorization, parallelization, etc. Then you have different algorithms coupled with those things. So during this the development of computer and the development of your simulation, we get this new concept and also this new algorithms case. And this concept and algorithms are not just for the computational physics, actually it's also applied to other fields. Okay, like in statistical physics, there are lots of problems, like mentioned by Patacha the other day. All right, so how about the quantum systems case? Okay, now in quantum systems case, we want to understand the physics or underlying mechanism behind those novel states. The typical case is in the phase diagram I'm showing here. This is supposed to be, as people think, is a phase diagram of the high transition temperature superconductors case. Now, during this phase diagram, you observe many these fascinating phases, such as antiferrometric states, superconductivity, okay, maybe the existing of supergap, and may have some quantum state as spin liquid, etc. Those already several talks already mentioned this. Yeah, and also you have this quantum criticality may be to observe the case. All right. Now, how can we understand this fascinating phenomena? The lesson we learned is that you have to take care of many-body interactions case. Okay. The old days, you always make a mean field approximation, make a complicated system into a one-body system, then solve it. However, our experience told us, okay, it's not going to be that way. If you want to understand the new phenomena, if you want to explore new states about novel phases, you have to be able to deal with many-body interaction. And this is a typical model. The other day, one speaker already mentioned, it's a Hubble model. You can mimic, you can simulate on optical lattice. Now, this is a fermion model here case. It's a simple model to understand the correlations because it's only 2 terms, kinetic energy and potential energy. Right? And the correlation came because you cannot diagonalize the kinetic energy does not commute with potential energy. All right. So let me give you briefly what we understand now. Even though all kinds of mean field approach can be applied to this model, and you can get all kinds of things you like to get, however, there's no consensus on the superconductivity whether it exists or not in this model. Okay. The quantum Monte Carlo result also shows different, will reach different conclusion based on from which angle you will look at this. Okay. So understand the many-body character of a Hubble model, whether it can give you superconductivity or not, is still an open and very challenging questions to answer case. All right. So scientifically, we always to ask ourselves, does the model capture initial physics? Because when you write down the Hamiltonian, not necessarily the terms you write down is what really happened in a system. Can one obtain or computable, useful information from the model? And the problem is that very often these two things are mixed. Okay, because suppose I have a model, but I don't know how to calculate. Then I cannot test by the answer whether the model is correct or not. Okay, so these two things were mixed. So once we deal with this difficulty there, now we need to get some help. And at this time, there's no like a simple way or unique way to deal with the problem. So people are doing all kinds of, trying all kinds of approach, try to solve this, to simulate many-body effect like here. All right. Now, typically, you have two ways to do these things. That's just from my understanding is one is the density functional theory. Okay. This is particularly useful when you try to design new materials case. And with this well-documented DFT, you can make some changes. Okay. Again, there are some difficulty because DFT is, in principle, Hodge-like. It's still making some local approximation, and when you do this lattice regularization, try to obtain correct crystal structure, you're still dealing with local minimum. You're not global minimum. So you have to find a way to reach global minimum. This depends on how you set up your potential, pseudo-potential. Okay, if you are dealing with finite temperature, you are working at extreme conditions, such as high pressure or strong magnetic field, then things could be very different, and then you have to take care of those conditions in that case. And the other way is try to use a model to do the simulation, such as Hubble model. In that case, you perform some kind of exact solution, okay, on a small lattice, then you do quantum Monte Carlo simulation on a large lattice. Okay. The difficulty there is you are dealing with quantum systems, so you are dealing with operators, not just numbers in that case. So it makes your computation much more expensive. Okay, you have a huge number of degrees of freedom to deal with. You have to make correct assumption or correct this separation of different energy scale, and then you go on with your simulation. Okay, most ideally or most easily is you can do some kind of one-body mean field calculation, such as BCS theory. However, it's often the case you don't know where this one-body Hamiltonian, effective Hamiltonian, is correctly described in the system you are studying case. All right, with time limit, I'll just go very quickly, just mentioning the challenge. Either you do DFT or either you do this model simulation, is still on how do you take care of many-body interactions in this case. All right, the interactions such as electron-electron interaction, electron-phonon interaction, and even electron-proton interaction, and other types of interactions case there. All right. The most simplest way is try to exact generalization, where you set up a basis, solve the Hamiltonian, then you get the answers there. However, you find that the system size increases exponentially. Okay, so you have this exponential wall to deal with. So you have to go on different approach. While different approach, you also meet the other problem. For example, if you do quantum Monte Carlo simulation, you'll find that you may deal with so-called negative problem. So still people are trying to figure a way to cure this negative sign problem. And one way maybe is try to use this machine learning, or maybe use a kind of quantum simulator, such as you do some simulation on the real system by design as an optical lattice there. So in my opinion, in the next 10 or 20 years, people should still working very hard, try to overcome such things like a negative sign problem or those model frustration, etc. And the problem is, I think, with the rapid development of computer hardware, and also people now pay attention to find new algorithms. So the development of software, it's probably possible we can solve the problem. I think I'll stop here. Thank you.
Thanks for your talk. So we open for a few questions or comments. Yes, there is one here.
Good afternoon. Thank you for your presentation. I want to know your personal opinion about machine learning. Machine learning or deep learning, probably they are suitable tools for finding best models.
Yes.
What's your personal opinion about this?
Thank you for your question. Actually, I didn't have time to talk about this. Actually, machine learning is also one way may help us. Because, for example, if we want to cure this so-called negative sign problem, we have this so-called, let me get this slide there. All right. So if we want to deal with this negative sign problem in a Monte Carlo simulation, there's one proposal is to use constrained path approximation. Okay, in that case, the workers will select a right path to avoid this negative sign. And now, how do you select this right path? Then you may be using machine learning. Okay, so each machine will pretend to be a worker. Then during the process working, he can learn how to avoid this negative sign problem. That's exactly, I don't have time to mention this. Yes?
Yes, another question.
So when you were discussing classical simulation and algorithm development, you mentioned that most classical problems could be simulated, assuming you had enough resources, which of course is quite different from the quantum situation, at least if you want to do a direct diagonalization where you can't have enough resources. But what I'm wondering is, can you give us some insight as to what would distinguish the kinds of classical problems that could not be successfully simulated, as opposed to the larger category that you said where most could? What makes something be in this unusual category of a classical problem that can't be?
You mean cannot be solved?
That cannot be solved, right.
We have thought of this negative sign problem may relate to some entanglement between the states there. So if we don't have, when we do the simulation, what we do usually is translate a d-dimensional quantum problem into d+1 classical problem. And then we deal with a matrix, etc. But in those things, maybe we should do differently. And if we cannot do those kind of transformation, mapping d to d+1, then probably is what you call cannot be solved by using computer.
Well,
I don't know if,
I was more wondering about the classical case as opposed to the quantum case.
No.
You implied that there were classical problems that could not be solved by a computer algorithm, even with sufficient resources. So what I'm wondering is what distinguishes those classical unsolvable problems?
Okay. In my opinion, any two-body interaction problem can be solved, classical problem can be solved by computer. However, three-body interaction or more probably cannot be solved.
Okay, well that almost sounds like the usual thing that we were taught since we were children, that the two-body problem is easy and the three-body problem isn't.
Right. But I think with enough computer resources, any two-body problem should be able to solve, really. So I don't see anything classically you mentioned cannot be solved.
Okay.
Yeah.
Okay, are there further questions or comments? One more? Yes?
I just want to find your opinion on the challenges relating to verification and validation of computer models.
I missed the first word. What?
The verification and validation.
The application and validation of
computer models. How do you verify codes? How do you validate them?
Okay, all right.
And in particular, where we don't have yet experiments.
Yeah, thank you. Yeah, sorry, I missed. All right. Now, there are two ways to do it. One is you test your algorithm or you test your program on a software model where you have analytical solution, it can be done. or for complicated, like a many-body problem, where you cannot solve analytically, you make some measurement in calculation, then compare with experiments. That's what you testify your model, testify your program.
One more question? Two more questions.
So thank you for the talk. I was just wondering if what is the progress of algorithms in terms of, so what I'm getting at is that typically when we want to show quantum supremacy, we will look at a problem that can be solved on a quantum computer but not on a classical computer. But every time we do that comparison, it turns out that there could be improvements in classical algorithms that could speed up the whole thing, and then the supremacy no longer holds. So what is your 10 pence or 2 pence worth of that?
Yeah, all right. Actually, right now, there exists no real quantum computers. Okay, what the D-Wave company got is kind of simulation. There's once they can design a way to find or search something like a global minimum quickly, then you can always implement in the classical computers there. So if you want me to name a problem cannot be solved by computers by the classical computer, or it can be solved by quantum computer, my answer is no. I think the only thing, the difference is just speed. Okay, if you do like it's a large prime number, factorization, then in principle you have quantum algorithm or quantum computer, you can do faster. But if you do this wave using this fast Fourier transform, you also can factorization very fast on a classical system. So I actually don't have a good answer actually to your questions here.
There was another question there.
If we regard a lot of engineering as a kind of classical physics, simulation has taken over from experiment to quite a large extent in, for example, aeronautics and flow physics. And experiments, because they're expensive, are only performed in order to validate the codes. Do you see this happening in areas like DFT with atomic force microscopy starting to be used to validate codes so that then the envelope can be pushed using the simulation?
Yeah, we just like we do theoretical physics, we will usually start with a few limits where we know the answer or we have some kind of intuition what the correct answer is. Also, simulation it must be based on some model, and the model usually should have some kind of symmetry. Okay, so with some conservation to observe, and those are the validations we would first try to make sure the program are correct.
Okay, so I don't see more questions or comments, so we thank the speaker again.
Thank you.
And all the speakers of this session, and I think that I have to change the chair.